All right, in this last video for chapter 8, we're going to talk about a reaction for hydrocarbons called combustion reactions. So the main use of hydrocarbons are fuels. So the hydrocarbons, the primary source for those are crude oil. So if you've ever heard of crude oil, that's where we're getting our hydrocarbons from. And crude oil is a mixture of a bunch of different hydrocarbons that we extract from underneath the surface of the earth. As a mixture, it's not very useful, and we have to go through a process called distillation to separate it out. And distillation is a method for separating compounds based on their boiling points, which we have talked about. Here, we're going to assume these are all alkanes just for the sake of conversation. Notice that up at the top of this picture, we have hydrocarbons that are 1 to 4 carbons long, and they have a relatively low boiling point. Next group down, 5 to 10, slightly higher boiling point. So as our molecules get bigger, the boiling point gets higher, which is exactly what we talked about earlier in this chapter. So because these boiling points differ, we are able to separate the different hydrocarbons out. Also pay attention to some of these examples, things you've probably heard before. So gasoline, we use that in our cars. Refinery gas up at the top, one good use there is natural gas, which is usually methane, just 1 carbon. Kerosene, use that for camp lanterns and heaters sometimes. Diesel, a diesel vehicle. Lubricating oil, so the motor oil you put in your car. Fuel oil, here we're talking more like airplane fuel, jet fuel, things with longer carbon chains. So anytime we burn these fuels, we're going through a process called combustion, which we'll get to in a second. So a few more terms with respect to this distillation setup. We've got what's called bitumen. That's down here at the bottom. Those are your very long carbon chains. So anything that has more than 70 carbon atoms we'll define as bitumen. Each of these individual pieces that we've already mentioned, each one is a fraction. So the individual piece coming off of the distillation. And then another term related to this that you've probably heard of before is octane rating. Now, because we know how to name hydrocarbons, octane would be the 8 carbon alkane that is not related to the octane rating. So octane rating is a scale that indicates how well the fuel is going to burn in your vehicle. Okay, notice octane isn't even part of the gasoline fraction. Now, if you looked at those different uses of each fraction, some of them we use a lot more frequently than others, usually some of the smaller hydrocarbons. So the longer hydrocarbons being less useful, we can make them more useful by going through a process called cracking. So here what we're doing is we're taking a longer carbon chain. So in this equation example, we have C18H38, and we're going to break it apart into smaller pieces or crack it. So in this case, we're getting a couple different pieces off, and what those exact pieces are is not important here, but the main idea with cracking is you're taking a long hydrocarbon, you crack it, and you make short hydrocarbons. The other thing to notice is we're going from an alkane to some alkenes as well as an alkane. So you get a mixture of hydrocarbons in this cracking process. Things to know is it takes a lot of heat and a lot of energy to actually break these hydrocarbons down. But if we could get more useful hydrocarbons out of them, we will. So the main reaction that we're going to talk about are combustion reactions. And combustion reactions in general are when we turn fuel into energy. So when you burn gas in your car or when you burn wood in your fireplace, all of those are combustion reactions. We're specifically going to talk about complete combustion and learn how to write those reactions. Now, complete combustion is your fuel reacting with oxygen to make only carbon dioxide and water. So we have a very straightforward formula for our complete combustion. Your hydrocarbon formula can vary. It's the only thing that's going to change. Always mixing it with oxygen, and you're always making carbon dioxide and water. So the equation here, we have some Hydrocarbon, it could be an alkane, an alkene, or an alkyne. Doesn't matter. Mixing it with oxygen. Oxygen in the air is O2. It's one of our diatomics, so that's important to remember. We're making carbon dioxide and we're making water. Then the only difference, the other difference is balancing. The other type of combustion is called incomplete combustion, and with incomplete you're getting a bunch of different products because you don't have enough oxygen. Right, so you're still getting carbon dioxide and water, but you're also going to get things like carbon monoxide and smaller hydrocarbons that we observe as soot. So for incomplete combustion, know the general concept, but we will not be writing reactions because they're not predictable like the complete combustion reactions are. So here's some examples. We're going to draw the hydrocarbons using line angle structures first, just for some practice. It's not necessary for writing these equations, but we're going to do it just for practice. Then we'll write the complete balanced combustion reaction as well. So for the first one, we have hexane. Hexane, the prefix hex means we have 6 carbons. ANE means it's an alkane. So 1, 2, 3, 4, 5, 6. There's your structure. For the chemical equation, we know we have the 6 carbons. Again, you could go in and count your hydrogens, but we know it's an alkane, so it must be the 2N plus 2, which means there must be 14 hydrogens. Right? This has to react with oxygen and make only carbon dioxide and water. So that's how we know how to fill in the rest of the reaction. Then we need to go back and balance it. When we balanced reactions back in chapter 6, we did some of these as examples. So here we can practice them again. First we'll look, we've got 6 carbons on the left side, only 1 on the right, so I will put a 6 in front. 14 hydrogens on the left, only 2 on the right, so I'll put a 7 in front. Oxygen, I have 2 on the left. On the right, I get 12 from CO2, and I get 7, from the water, so that adds up to 19. To put a number in front of O2, I'd have to have the 19, which would be 9.5. Now remember, if you come up with a half like this, you need to go back through and multiply everything by 2. So we're going to have 2 hydrocarbons, 19 oxygens, 12 CO2s, and 14 waters. So there would be your balanced complete combustion reaction. Let's look at the next example, trans 2-heptane. Which again, here's a typo, sorry, heptene. So hept is 7, 1, 2, 3, 4, 5, 6, 7. Trans, double bond starting on carbon number 2, puts it right there. For the formula, we have C7. We have 1 double bond, so it has to be 2N. So there has to be 14 hydrogens. Again, it has to be plus oxygen, making CO2 and water. To balance this, again, we'll start with carbon and work our way through. So there is a shortcut to know whether or not you're going to have to multiply by 2 like we did in this first example. If you catch this shortcut, it could save you time. If you don't and you come up with a half at the end, you just multiply everything by 2. But the shortcut is if the number of hydrogens is odd, half of the number of hydrogens is odd, so 14 divided by 2 is 7, then I know I'm going to have to multiply by 2 because you're going to end up getting an odd number in front of water, which is going to give you an odd number of hydrogens. So if I look at my current example, again, I have 14 hydrogens, so I know I'm going to have to multiply by 2. So I'm going to go ahead and put a 2 in the front, and that means now I have 2 times 7, which is 14 carbons, so I'll put a 14 in front of CO2. Hydrogen, I've got 2 times 14, which is 28. So if I have 2 on the right, I'll put a 14 on front to get 28 hydrogens. Now oxygen, I have 28 of them from CO2 plus another 14 from water. So that's going to be 42, which means I'm going to need 21 times 2 to get 42 on the left. And there's your balanced reaction. Go ahead and try the last example on your own. See if you can write the structure as well as the balanced complete combustion reaction. All right, 3-octane. Again, I like to start with the triple bond. So I know there's number 3 and 4. So there's 2 and 1, 5, 6, 7, 8. So there's a version of 3-octine. Oct means we have 8 carbons. It's the triple bond, so it's 2n minus 2. So that means we're going to have 14 hydrogens. Complete combustion, we react with oxygen, make carbon dioxide and water. Again, this is all coincidence, but again I have 14 hydrogens, so half of that is odd, so I know I'm going to multiply by 2. This time 2 times 8 gives me 16 carbons. 2 times 14 is 28, so again I need 14 waters. So now I've got 32 oxygens plus 14 oxygens to give me 46. Half of 46 is 23, and there's your balanced reaction. So here's a quick concept check for all of Chapter 8. There were 8 videos in total, so go through and make sure you can answer each of these questions. And if you can, you've got a pretty good grasp on what you need to do for Chapter 8. And in the printed slides and also in Canvas, you've got the learning objectives written out that you can treat as your study guide.